Physics, part 218. For many oscillators, the graph is approximately a sine or cosine curve. A sinusoidal displacement time graph is characteristics of an important type of oscillation called simple harmonic motion, SHM. Oscillators which move in SHM are called harmonic oscillators. We shall analyze simple harmonic motion in some detail because it successfully describes many oscillating systems, both in the real life and in the theory. Fortunately, the mathematics of SHM can be approached through a simple defining equation. The properties of the motion can be deduced from the relations between graphs of displacement against time and velocity against time, which we have already met in chapter 3. Well, now we've got another section here, and it is simple harmonic motion. Simple harmonic motion is defined as the motion of the particle about the fixed point such that its acceleration A is proportional to its displacement x from the fixed point and is directed towards the point. Mathematically, we write this definition as A is equal to minus w square into x. Where w square is a constant, we take the constant as squared quantity, because this will ensure that the constant is always positive. The square of a positive number or a negative number will always be positive. Why worry about keeping the constant positive? This is because the minus sign in the equation must be preserved. It has a special significance because it tells us that the acceleration A is always in the opposite direction to the displacement x. Remember that both acceleration and displacements are vector quantities, so the minus sign is shorthand by the idea that the acceleration is always directed towards the fixed point from which the displacement is measured. This is illustrated in the figure 2. The defining equation is represented in a graph of A against x as a straight line of a negative gradient. Through the origin, as shown in the figure, the gradient is negative because of the minus sign in the equation. Note that both positive and negative values for the displacement should be considered. The square root of the constant w square, that is w, is known as the angular frequency of the oscillation. This angular frequency w is related to the frequency of f of the oscillation by the expression w is equal to 2 pi f. By Newton's second law, the force acting on a buoy is proportional to the acceleration of the body. I beg your pardon, please, and let me correct my sentence. By Newton's second law, the force acting on a body is proportional to the acceleration of the body. The defining equation for simple harmonic motion can thus be related to the force acting on the particle. If the acceleration of the particle is proportional to the displacement from a fixed point, the resultant force acting on the particle is also proportional to the displacement. We can bring in the idea of direction of the acceleration by specifying that the force is always acting towards the fixed point, or calling it a restoring force. Solutions of equation for simple harmonic motion. In order to find the displacement time relation for a particle moving in a simple harmonic motion, we need to solve the equation A is equal to minus w square into x. To derive the solution requires mathematics which is beyond the requirement of A and AS physics. However, you need to know the form of the solution. This is x is equal to x0 sine w into t, or x is equal to x0 cos w into t.